All right, so yeah, we do have this exam coming up a week from today. Again, being in this class, you should plan on coming to class here next Friday to take it instead of an alternative time for the online class. As I sent you the note yesterday, I sent you a note with a bunch of problems on the test, descriptions of the types of problems. I'm not quite done. I think I'm probably going to put one more question on for sure, maybe two. We'll see. Over the weekend, and then I'll send you information about that extra question or two over the weekend. I also want you to note on Moodle that I just opened up a new section this morning, actually, called Optional Instructional Videos for Chapter 2 down here. So these are the ones for Chapter 1, including the ones that I said were pretty highly recommended about bifurcations. Chapter 2 videos are in this section. These videos focus on two main models, interacting species and harmonic oscillator models. They're more topical, focused on those models than they are sort of a section-by-section account of Chapter 2. But I think if you want more information about those concepts, those will be valuable to you. I also am going to have one more extra reading assignment. I'm working on it right now. Let's see what's due for next Monday right here. Here's what I highlighted. It's going to be another new extra reading assignment, number 3. This will be the last extra one before the exam. I need to work on that still, finish it up. By the looks of it, as I'm writing it here, it's probably not going to be as long, but the topic will still be difficult. So hopefully I'll be able to post that over the weekend, and again, I'll talk about things that you might need to know for that on the test. One of which I already did mention. I mentioned there will be a problem related to the full solutions and the flows. And the main thing I'll try to emphasize about that today is that with this flow idea, you can, for autonomous equations, especially when the solutions don't have any vertical asymptotes, you can try to understand what happens to the y-coordinates of solutions by iterating that flow function. It's called a flow math. Just like you iterate for Euler's method, you can iterate functions by reapplying them over and over again. That's the basic idea. All right, lots of things to do today. I want to start off by just showing you how you can use Mathematica to do a harder bifurcation example. If you want to write that down. All right, there's a 5th degree right-hand side function. It is autonomous. There's no t's in the right-hand side. Y is the dependent variable for the solution. And it's the independent variable for the right-hand side function, if you ignore the differential equation. There's a parameter involved in alpha. I made this difficult in 2 ways. I made it a 5th degree thing here. And I've also put the alpha in a couple different spots, right there and right there. All right? I would not want to try to find bifurcation values for this kind of example without technology. And Mathematica can be programmed essentially to do it pretty quickly. If I use solve in conjunction with table in this way, with this replace all operator in ways I won't explain. Question?
In your function definition, do you want a y after your -2 alpha?
Yes, thank you. Which is going to make the example different than I was thinking. Let's see what it produces anyway. Anyway, without explaining what this code does, well, I can sort of explain what this output looks like. If I do EQ PTS of some particular value of alpha, like 1, I will get some symbolic representations of the equilibrium points, some of which could be imaginary numbers or complex numbers, I should say. And so we won't see them on a real number line. If I do //n, I can approximate those, yes. All but one of them is complex. Just this one is real. For different, if I can actually plot this as a function of alpha. That's what I'm doing here. I'm putting those things in alpha, and the 1, 2, 3, 4, 5 just picks off the 1st, 2nd, 3rd, 4th, and 5th of those. Let's see. This is going to be very interesting looking. It takes a little while to plot because it's doing a lot of computation. Oh yeah, that's interesting enough, I guess. Okay. what do we have here? What is this graph? This is again showing a graph of how the equilibrium points depend on alpha. What is alpha again? Alpha is this external parameter. So what you want to imagine if you graph the equilibrium points as functions of alpha is this helps you figure out what phase lines look like. Notice how the axes are labeled, alpha horizontal, y vertical. So your phase lines are going to be vertical here, and you have a bunch of them. Infinitely many, in fact, as alpha changes. You get a different phase line for each value of alpha. When alpha's over here, less than about negative 3.6 or 3.5 or so, maybe negative 3.6, you're going to have 3 equilibrium points. Not clear whether they're sync sources or nodes yet, but there's going to be 3 of them. As alpha continues to increase up to about negative 3.6 or so, evidently that's where the bifurcation occurs because those 2 equilibrium points come together and annihilate each other. And in this regime here, between about negative 3.6 for alpha and about positive 1.4, you just have 1 equilibrium point. And over here you have 3 again. There's another bifurcation curve that occurs at about 1.4 or so. You can animate this. You could use contour plot in this kind of way, set f of alpha of y equal to 0, to draw the graph of these curves, really. These curves are where you have equilibrium points, so they're going to make f's of alpha of y equal to 0. I can use contour plot as another way to plot that actually more quickly than what I did up here. And change my mistake. Put stuff times y in there. And by including also a contour plot where alpha is a constant, remember alpha is the horizontal axis here, we also can animate the phase line. In other words, animate where that vertical line is. So we are, again, looking at different phase lines for different values of alpha. Again, it's not clear what's sync source or node yet, but we can ultimately figure that out. What do you think the best way to figure that out is, where things are sync sources or nodes? And this was the thing I was asking you to answer the other day, and people were taking a long time. Well, you should have. Yep. Plot. Well, the derivative will help, but the original function is fine as well. Plot the right-hand side function. That's what I meant. Not that. Don't think of it as the derivative of the solution, though it does give you slope values for solution curves at various points. Plot the right-hand side function. Fix my mistake. As alpha changes. So there you can see when alpha is negative 4, for example, you've got 3 roots to the right-hand side function corresponding to the 3 equilibrium points for the phase line. As alpha increases, what do we guess for the bifurcation value? About negative 3.6. What happens? 2 equilibrium points came together and merged in the phase line. That corresponds to the 2 roots of the right-hand side function coming together and annihilating each other. Looked like there was another equilibrium, bifurcation value at about 1.4, close to 1.5 perhaps. Yes, as alpha continues to increase, eventually that happens. Try typing in 1.4 here. Not quite 1.4, a little higher. Less than 1.5. We get the creation of 2 roots to the right-hand side function, which corresponds to the creation of 2 equilibrium points to the phase line, and 2 more equilibrium solutions in the slope field for the differential equation. All these things are tied together in what initially seems like confusing ways, but if you keep working at it, it'll become less and less confusing. You want to go back and forth between these things. Exactly. How could you find these bifurcation values exactly? Well, it's probably pretty hard to represent them exactly, but I will say we can approximate them. The key thing to realize here is that the way these bifurcations typically occur, and this is just a typical thing, it doesn't always occur this way. The way these typically occur is when the points merge and annihilate each other or get created, in a sense, and that's going to happen when your not only does your right-hand side function have a root at one point, and it's a double root in that case, what else will say that that's a double root? It also will also mean the derivative of the right-hand side function will be 0 there. So not only do you have a root there, but you also have a critical point, a local min or a local max. I should really say a local min or a local max instead of a critical point. So if we solve a system of equations, I'm going to use nsolve to do this, where both the right-hand side function is equal to 0, and its derivative is equal to 0, that should hopefully give me both the value of alpha, where I have bifurcation values, and the corresponding y coordinates of the equilibrium points. If I solve this for both y and alpha, hopefully nsolve can do this, I will get approximate values for bifurcation values for alpha and the corresponding y coordinates of equilibrium points. There's a bunch of roots of that system of equations. That's a system of 2 equations and 2 unknowns, y and alpha. A bunch of solutions, many of which are complex numbers, but a few of which involve only real numbers. For example, alpha equals negative 3.53129. Corresponding to y equals 2.4048. That's almost what we're looking at right here. If I replace this negative 3.55 with negative 3.53129, we are going to be essentially very close to that bifurcation value. That is a good approximation for the bifurcation value. The graph there is just barely touching the y-axis approximately. If I reduce this actually down to, let's see, the approximation is negative 3.53129. If I made it negative 3.5313, or 13, then you'd see 2 equilibrium points on the right, though they're so close together they look like 1. Do we find the other bifurcation value, approximately? I hope. Scanning through here. Do you see any of the real ones? I'm not. Oh, here it is. Yeah, 1.4985, close to 1.5. 1.4985. Looks like that bifurcation is right about at that value of alpha. That's the bifurcation value, and the y coordinate of the point where you have the equilibrium is close to 0.515, as you see there. And if we went a little higher than that, we more clearly see 2 equilibrium points. Make this a 6, for example. Maybe we can see them. Well, they're still pretty close together. If I made it 1.5. Okay. Get them a little further apart. There we go. But if I go below that bifurcation value, below 1.4985, like 1.4984, we won't see any. We don't see any of it. It hasn't touched and crossed the y-axis there yet. So the main point is solving the system of equations in general helps you find bifurcation values of alpha and the y coordinates where you get the equilibrium points merging. Approximately. It's a typical kind of bifurcation. There are other kinds of bifurcations that occur, but that's a typical kind. All right, you're not going to have a homework problem like that, by the way. Okay, that's just for your information for the future in case you ever need this. Let's do another method of undetermined coefficients example. And our next thing to do today let's make it that one. That's non-homogeneous because you've got a function of t over there that's not being multiplied by the y. It is linear. It is of the form a of t times y plus b of t. The a of t is the constant function 3 in such a situation, we actually call this a constant coefficient linear equation. The B of t is nonlinear, but that doesn't matter. The equation is still linear in y. We still call it a linear equation. I think I'm going to delay my proofs related to this stuff until next Monday, because we have a lot of other calculations to do today. So we're going to do some proofs on Monday related to this. Study the book's proofs. That'll help you understanding the proofs we do in class. It is linear. It's linear in y. And we can consider the associated homogeneous equation where you get rid of the b of t. It's not the same equation as the original. That's the original. That's the one we want to solve. This is just an associated equation that's easier to solve by guessing even. It's not always something where you can guess, but a constant coefficient like this, it is easy to guess. And we're going to use the corresponding guess that we make, which we call y sub h, to help us ultimately construct the solution of the original, through also guessing a y sub p for that. Y sub h here is a constant times e to the 3t, okay? That's an example you should be able to do just like that. That's the general solution for it. What about yp for the original equation? Go back to the original non-homogeneous equation. It turns out to be a good idea. I mean, you don't really have to do this, but it turns out to be a good idea for conceptual sake to rewrite the equation in the following form for the purpose, for one, of guessing perhaps more easily, and secondly, I'm going to show you a new technique in a few minutes called the method of integrating factors, and it's better to have the equation in this form in order to use that method of integrating factors. When you write it in this form, sometimes you think of the left-hand side as what's called a linear differential operator, which is kind of a fancy name. Essentially, you can think of it as something that's telling you to take whatever function you're thinking of, guessing for example, and differentiating it and subtracting 3 times the function to get some new function. And what you want to solve the differential equation is you want that new function to equal cosine of 2t. So once again, this is educated guessing. It's not random guessing. You better guess a trig function. Would it make sense to just guess some constant times cosine of 2t? That's maybe, you're getting closer at least, you're getting warmer. However, if you guess some constant times cosine of 2t, a sine of 2t will come into play. And you might wonder whether we're going to be able to cancel it. And we wouldn't because we'd have a cosine there. So should I guess sine of 2t? Well, then you'd have a sine there. So what you want to guess in this kind of situation is actually what's called a linear combination of cosine and sine. Some constant times cosine plus another constant times sine. What do you think I should guess for the arguments of cosine and sine? 2t. Don't guess 5t. So there's yp. What's yp prime? dyp dt. I'll use prime notation here. To differentiate, a and b are constants. You're going to get, from the chain rule, negative 2a sine 2t plus 2b cos 2t. Now substitute this into the left-hand side. The left-hand side, this differential operator, in this case, when you plug in yp, can be written as yp prime minus 3yp. I could put the extra step in of plugging these in without combining the cosine and sine, but I hope you can do this in your head. You're going to have some constant involving a and b times cosine of 2t plus some other constant involving a and b times sine of 2t. The constant in front of the cos 2t is going to be the coefficient of the cosine for the yp prime, the 2b. minus 3 times the coefficient of the cosine in the YP equation. Minus 3a. It is easy to make mistakes here, so you gotta be careful. I can make mistakes too, so I have, so catch me as you've been doing. It's been good. How about the sine term? We got the yp prime has a negative 2a in front of the sine term. And minus 3 times yp will be minus 3b. Is that helpful? What do you think here? Got any intuition about whether this was helpful to do? Yes, and why?
We can set the, it would be the 2b minus 3a to 1, and then the negative 2a minus 3b to 0.
Right. The right-hand side of the original equation is 1 times cos 2t plus 0 times sine 2t. You don't have to write that in your notes. So you want to choose a and b so that this is 1 and that's 0. That's a system of 2 linear equations and 2 unknowns. Does it have a unique solution? Yes, it will in this case. Let me write it as this. Negative 3a plus 2b equals 1. And negative 2a minus 3b equals 0. Took that and switched around the a and the b term. Set it equal to 1. Set that one equal to 0. That's a system of 2 linear equations. They're not, these equations are not, well, the left-hand sides are not multiples of each other, constant multiples. There will be a unique solution. If you know, if you're taking linear algebra, you would know about that. You can solve this in 2 ways, typically. You could try to multiply these equations by some constant and then add them in such a way that you cancel either the a or the b. That's called elimination. In linear algebra, that's the thing you focus on. You end up doing what are called row operations, essentially. You can also use what's called substitution. I think I'll do it that way. You can solve either of these equations for one of the unknowns in terms of the other. For example, well, it's easier to use the one with 0. This equation would say 2a equals negative 3b. Positive 3b? No, this is right. I'm bringing the 2a to the right.
Sorry, I thought you had negative 3b.
I'm glad you're being alert, though. Thanks. Divide both sides by 2. A is negative 3 halves times b. I'm going to double check these in my own mind here. Then you can take that and substitute it into the other equation in place of the a to get an equation only involving b. After doing so, you get that, which simplifies to what? Let's see, negative 3 times negative 3 halves is going to be positive 9 halves. Plus 2, 9 halves plus 2 is 13 halves. 13 halves, b equals 1. So b is 2/13. Now use this one to figure out a. A is negative 3 halves times b, so a is going to be negative 3/13. You can check it by substituting back into the original equation. You can also use solve in Mathematica as another way to double check it. So plug those numbers back into the original system of equations, both equations. So negative 3a plus 2b equals 1, and negative 2a minus 3b equals 0. Solve for a and b. All right, we'll try. Not quite done with the problem yet, though. The fact that this equation is linear is going to imply that if you add yh and yp, you get the general solution of the original linear equation. That takes proof. That's what we'll focus on proving on Monday. To say that if you've got a linear equation like this, YH plus YP would give you the general solution of the original. General solution of original. Y equals YH plus YP. Are we doing that on the camera? Okay. C e to the 3t. A is negative 3/13. That's the coefficient of cosine. So minus 3/13 cos 2t. B is positive 2/13 plus 2/13 sine 2t. So okay? Okay, that'll be the general solution. You can use it to solve any initial value problem. If you've got your generic initial value problem, y of 0 equals y sub 0. You're going to get the equation y sub 0 equals c times e to the 0, which is 1, so you just get a c. Cosine of 0 is 1, sine of 0 is 0, so you end up getting just a minus 3/13 here. And you can add 3/13 to both sides then to say c is y0 plus 3/13. That'll be the c for a generic IVP. Should we check it with d-solve value? D-solve value. YP, y prime of p equals. I'll write it the original way. 3, you gotta put a y of t in Mathematica, even though it's a y by hand, plus cos 2t. Put a generic initial condition in there. There it is. You can multiply the 1/13 through by doing / expand. Yeah, negative 3/13 times cosine 2t plus 2/13 times sine 2t. That's the yp part. This is the YH when C is Y0 plus 3/13. Yes. Okay. All right. Let's move on to that next method, the method of integrating factors. And we'll do it in the context of a mixing problem. I said there will be a mixing problem on the test. Let's say we've got a really big vat this time. It can hold 100 liters. I'm trying to make this make sense to people outside of America, so I'm kind of avoiding gallons and so forth. And say we start off with 20 liters of pure water to start with. Pure water, pure H2O at the start, at time 0. And at time 0, we start letting water, salt water come in and get mixed instantly, really well. That's the assumption at least. And we also open up the drain so that we're mixing salt water, but we're letting salt water go out too. What's the flow rate up here? Let's let it be 5 liters per minute. That's called the flow rate. I'm not going to write that out, but you can write it out. That's the flow rate. The use of the word flow there is different than the use of the word flow with the other thing, which I'll still talk about today. That's a flow rate in. We need a certain concentration of salt. I don't know what's a typical concentration for salt. Let's just pretend it's 10 grams per liter this time. G is grams here. It's not gallons, it's grams. We've got an outflow as well, and we're not going to make that be the same. We're going to make it be smaller. 4 liters per minute. Let Q equal the quantity of salt in the tank in grams. T equal time since the start of this process in minutes. We could let V be the volume of fluid as well. That's going to come into the differential equation. It's also a function of t, and in fact, it's a pretty simple function of t. What would it be? You don't have to do a differential equation for it. Look at the picture, look at the flow rates.
Just t.
20 plus t, yeah. T plus 20. 20 liters to start off with for the volume. And the volume is increasing by 1 liter every minute because you take 5 minus 4. The net inflow, taking into account both the inflow and the outflow, is positive 1 liter per minute. Multiply that by t minutes, you're going to get something in liters. It's like there's a coefficient of 1 here. That would be in liters per minute. And t itself would be in minutes to give you a volume in liters. Based on that information and based on the basic common sense principle that the rate of change of the quantity should equal the rate in minus the rate out, we can come up with a differential equation. Rate in is 5 liters per minute times 10 grams per liter to give you 50 grams per minute minus four liters per minute. That's the flow rate out. What's the concentration? This is the hardest part. Q over V. You leave the Q as a Q, and don't put a T when writing it by hand. We could write V as V of T, and that would be okay to do actually. But we do know a formula for V, it's T plus 20. That would be that's a concentration in grams per liter. These multiply together to give you 4Q over T plus 20 in grams per minute. You want the units to be grams per minute because that's what the units for dq dt are. All right, so that's a differential equation. It is actually linear, so theoretically we could use the methods of section 1.8, though we would find guessing the YH a little trickier because we'd have to use separation of variables to find the YH. However, we're going to use a different method, and you should know this method for the test as well. The method of integrating factors. What we do is we rewrite the equation to put the term involving the Q on the left side with the dq dt, just like we did when we guessed the YP in the previous example. I'm also going to write 4Q over T plus 20 as 4 over T plus 20 times Q. That's going to be helpful to do so. And on the right-hand side, we just have the 50. By the way, we do have an initial value problem here, too. What's Q of 0? 0. Pure H2O at the start. Didn't have to be 0. I could have a certain number of grams of salt in there at the start. Let me tell you what the method is. So we're running low on time. The book does motivate where it comes from. It's going to be, it's kind of a mysterious method. Okay? I'm just going to show it to you. The book in the reading, which you should read, does explain why it works. And I hope you have the desire to understand why it works. We're going to create a new function, labeled with the letter mu, typically. That's the traditional thing to label it with. It is a function of t. Not going to bother writing the t. I could. It's kind of a strange function. It's e to the indefinite integral of that thing the thing in front of the cube. That's why I separated it to be in front of the cube. Weird, huh? When I write an indefinite integral, remember that really means infinitely many functions. So there are really infinitely many things that could work from you, though you typically try to pick the simplest one. Pick the simplest antiderivative here. Don't worry about absolute value signs. Don't worry about putting a plus c. Use c equals 0. That can be simplified. E and natural log are inverse functions, but before I use that fact, what should I do? Put the 4 up in the power of the t plus 20 in the log. Then I can make use of the fact that e to the x and natural log of x are inverse functions to say this function, this integrating factor, simplifies to t plus 20 to the 4th. It's called an integrating factor. Why? Well, you end up multiplying the original equation by that on both sides to get a new equivalent equation. And then it turns out that that equation will be easier to somehow integrate. That's why it's called integrating factors, right? The word factor means one of the terms in a product. And then we're going to use it to integrate. So what happens when I multiply both sides by t plus 20 to the 4th? Well, it seems to make things worse. The equation ends up looking more complicated. However, it's actually better. Don't forget to multiply it on the right-hand side as well. More complicated looking, it's actually better. Why is it better? You have to look at it in the right way. Really concentrate here. Did I make a mistake?
Maybe.
Cube.
Yeah.
Yeah, okay. T plus 20 to the 4th times dq dt plus 4t plus 20 cubed times q. Hey, these things, that's kind of related to that, isn't it? That is the derivative of that. And because of that, overusing the word that, this expression on the left-hand side is a function times a derivative of another function plus the derivative of the first function times the other function. Which should remind you of the product rule. That left-hand side is the derivative with respect to t of t plus 20 to the 4th times q. And q is a function of t. I could put q of t in there. And that would be okay, but I'm not bothering because you should be okay with not bothering to put it. And hey, because it's the derivative of that, it's easy to integrate. You integrate it, you just get that. It's like magic. Not any old factor will do. This formula and its particular form are important to make that work in ways I'm not explaining right now. You should read the book. Maybe we'll have a tiny bit of time on Monday. So now you integrate both sides. This equals, oh, I forgot, did I forget something? Oh, I guess it's okay. 50 times t plus 20 to the 4th. Now integrate both sides. Integrate. I'm not going to bother putting an integral symbol though. Integrate. The left-hand side is simple to integrate. It's the derivative of this function, so when you integrate, you get that function. I mean, we are doing indefinite integration here. There's going to be a plus c, but I might as well just have it on the right side. I don't need it on both sides. When you integrate the right-hand side, it ends up being pretty easy. You don't have to expand this out. It's easier to integrate it if you leave it as is. Sometimes you might want to expand it out. That's easy to integrate as is. Divide by 5 and make this 4 or 5. Because this is a t plus 20 in there, if you did a substitution, u equals t plus 20, then d would be dt. It's a pretty simple one to guess. You're going to get 10 times t plus 20 to the 5th power plus c. Can you see that? Okay. That's almost done for the general solution. Now just divide everything by t plus 20 to the 4th. The general solution is going to be q equals, divide everything by t plus 20 to the 4th. I'm going to get a 10 times t plus 20 to the 1st. I can distribute the 10 through if I like, 10t plus 200. I also get a plus c divided by t plus 20 to the 4th. And you can use this to solve any initial value problem, including the one where q is 0 when t is 0. Can I do it in my head? Well, I better not. 0 equals q when t is 0, so you get 0 equals 10 times 20 is 200, plus c over 20 to the 4th. C is going to be a fairly big negative number. Negative 20 to the 4th times 200. 10 to the 4th would be 10,000, so 20 to the 4th would be what, 80,000? Negative 80,000 times 200. I think we're looking at negative 16 million there for C. I think that's right. You can double check it. I won't take the time to check it in dsolve value, although I will tell you that dsolve value writes it in a different form. Before I put it on Moodle, I'll use dsolve value and I'll use expand to make sure they're the same thing. Okay, so make sure you download these notebooks, by the way, and it's going to be beneficial for you to do so if you haven't. And you are going to need to use Mathematica ultimately for your project, and on the exam you need to know the code, so it would be good to practice it. All right, here we are at the last 5 minutes. Let's spend 5 minutes talking about this flow idea. So again, we're talking about this with simple examples. This is a hard concept. So we better keep it to simple examples, at least in class, and probably simple examples on the test. On the reading, I do harder examples as well. That's a simple differential equation. dy dt equals negative 2y. It's autonomous. By the way, this mixing problem is not autonomous, of course. It was linear, but not autonomous. There's the differential equation. If I add a generic initial condition to make an initial value problem, the solution, which I represent typically like this, the unique solution would be phi sub y0 of t equals y0 e to the negative 2t. All right? That's what you're used to. This is a function of t for any fixed value of y0. So we can animate it, we can make different graphs for different y0s, different graphs that are in the slope here. That are all solutions, no matter what y0 is. It does include the equilibrium solution, by the way, at 0. When y0 is 0, this is always 0. This generates what I call the full solution, where you still call it phi, you still have a variable t, but the y0 you call y and you don't make it a subscript anymore. Same expression to define this function, but I am thinking of the function differently. I'm thinking of this as really a family of functions, one function of t for each value of y0. I'm thinking of this as one function of two variables. But that one function of two variables has all the information I need to generate these solutions. I can go backwards if I like. This is kind of an intermediate thing to ultimately get to the thing I call the flow. Why did I use the fancy phi? I guess I didn't really explain that the other day. I'm using the fancy phi partially because I like it, and partially just to distinguish it from this phi, to sort of signify I'm thinking about it differently. That's why. It's related, but I am going to think about it differently, so I decided to use a different phi to emphasize that fact. That's why I'm doing that. It's a function of y for any fixed value of t. It's really a family of functions. And I put the t's in the exponent. I shouldn't have said exponent. Like they're in an exponent. Like that. They do act like exponents, as we will see, and as you'll see in the reading. It's the same expression that defines this function, or these functions. I'm just thinking of it differently. You're thinking of y as being the variable, t as being constant, and to emphasize that, in this example, it's good to write it that way. E to the negative 2t in parentheses in front of the y. A constant times y. And if I graph this as a function of y, it's going to be a straight line to the origin with slope e to the negative t. Which does generate different functions for different t's. Different slopes for different t's. By the way, in Mathematica, I found I had to do it as an over superscript, not an upper right superscript, because upper right superscripts in Mathematica are reserved for exponents. So I had to do it this way to get it to work. Different t's produce different linear functions. Okay? These functions all have a positive slope because e to the negative 2t is always positive, no matter whether t itself is positive or negative. But what's the value of this function? It's not a solution of the differential equation. The value comes that it can keep track of points, y-coordinates of points, in, say on the phase line, for example, with respect to the differential equation, not by plugging into the differential equation formula, though in a sense we're doing that, but by iterating this function. Let's get particular here in 2 minutes. Oh, we're about out of time. Give me 1 minute here. What I typically most like to do if I can, it's not always possible, because of vertical asymptotes, is I typically like to plug in t equals 1 and consider what's called the time 1 map. Plug in t equals 1. What are you going to get? You're going to get e to the negative 2 power times y as a function of y. Iterating this function keeps track of y-coordinates of solutions in autonomous situations where you don't have vertical asymptotes. That's the point. Okay? So for example, if I started with an initial condition of y0 equals 10, if that was my initial value for y for the differential equation, I can find the location of y, the y value 1 unit in time later, by plugging 10 into this time 1 map to get e to the negative 2 times 10. Which you may say, well, couldn't I have just done that with the original formula? And the answer is yes, you could. However, it is still a nice process here of iteration. And remember, my ultimate point is to use this in chapters 3, 4, and 5 for nice visualizations. We're going to iterate sets of points under this kind of mapping, and we're going to see how those sets change. y2 is found by iterating this function, applying it twice in this case, to ultimately get e to the negative 2 times e to the negative 2 times 10, which simplifies to e to the negative 4 times 10, which is the same thing you'd get if you plugged in y0 equals 10 and t equals 2 into that equation. So we are keeping track of the y coordinates, but I will say in 5 seconds, this doesn't work for non-autonomous when you keep iterating like this. For a non-autonomous equation in solution, this doesn't work. And you'll see some examples in the reading. Okay. Sorry we went a bit over time. See you on Monday. It's probably right? Yeah, okay, Monday.